All right, let's do this. You ready to get our hands dirty with some material science?
I was born ready.
Okay, good, because today's deep dive is all about how things break.
The stuff of nightmares for engineers everywhere.
You got that right. But seriously, it's also super fascinating. You sent over this chapter from a material science textbook, wanted the full breakdown on all things fracture, fatigue, creep.
The unholy trinity of material failure.
Exactly. So consider this deep dive your crash course on why things fall apart.
We're talking bridges, airplanes, maybe even that cookie you dunked in your milk a little too long.
Okay, maybe let's stick to the big stuff for now. No offense to any soggy cookies out there. But seriously, let's start with the basics. What exactly is fracture in the material science world?
Well, at its most basic, fracture is just what it sounds like. It's when a material separates, breaks into two or more pieces. And this happens because of stress.
The big break.
Exactly. But of course, it's never that simple, is it? There are actually two main types of fracture that we need to talk about: ductile and brittle.
Okay, so what's the difference? Like, is one worse than the other?
Think of it this way. Imagine you're pulling on a piece of chewing gum.
I can picture that.
It stretches and deforms quite a bit before it finally snaps, right? That, my friend, is ductile fracture.
So it can take a lot of abuse before it finally gives up.
Exactly. Ductile materials can absorb a lot of energy before they break, which is important because it often means you get some warning that something's about to go wrong.
Okay, I'm liking the sound of ductile so far. What about brittle?
Well, brittle is... Well, it's more like a glass window shattering. It breaks suddenly, with almost no deformation.
Okay, yeah, that's definitely less forgiving.
No kidding. Brittle fracture gives you very little warning, and those cracks can propagate super fast, leading to, well, catastrophic failures.
Yikes. So ductile good, brittle bad. Got it. But how can you tell the difference? If you're looking at a broken part, can you tell how it fractured?
That's where things get really cool. You need to zoom in, weigh in with a microscope. If you look at a ductile fracture surface up close, you'll see all these tiny dimples.
Dimples, like on a golf ball.
Yeah, exactly like that. Each dimple is a little void that formed and grew before the material finally gave way.
So it's like a microscopic record of the material's last stand.
Exactly. It's pretty amazing, actually. Now, a brittle fracture surface, it tells a different story. It'll usually look more crystalline or granular.
So it's all about how the material breaks down at the atomic level.
Precisely. And for engineers, understanding these differences is crucial. In most cases, we really want materials to be ductile, especially in things like bridges and airplane wings.
Right. You want that warning sign before something goes catastrophically wrong.
You got it. But here's the thing. Sometimes a material that's normally ductile can actually become brittle under certain conditions. It's called the ductile to brittle transition.
Oh, yeah, that sounds a little scary. What kind of conditions are we talking about?
Well, one of the biggest culprits is temperature. As the temperature drops, some materials can become much more brittle.
Oh, like those old World War II Liberty ships that would crack in half in the icy North Atlantic.
Exactly. They were built with steel that was fine at normal temperatures but turned dangerously brittle in the freezing cold. Those failures were actually a turning point in our understanding of how temperature can affect a material's behavior. It's why we pay so much attention to it now.
That's a pretty chilling example, no pun intended. So temperature's a big factor, but are there other things that can make a tough material go brittle?
Absolutely. The speed at which a material is deformed can also have a big impact.
Okay, I think I'm seeing where you're going with this. It's like if you try to bend a piece of metal too quickly, it's more likely to snap instead of bend.
That's the idea. And then there's the whole issue of stress concentrations. Any sharp corner, notch, even a tiny scratch on the surface of a material can act as a stress raiser.
A stress raiser, what does that mean exactly?
Think of it this way. In a perfect world, stress would be distributed evenly throughout a material. But in the real world, you always have these tiny imperfections, and those imperfections act like little amplifiers for stress.
So even a tiny scratch can make a big difference.
You bet. It's kind of like that saying, a chain is only as strong as its weakest link. That tiny scratch could be the weak link that causes the whole thing to fail.
Okay, I think I'm starting to get the picture here. Temperature, strain rate, and even those tiny imperfections can all play a role in whether a material breaks in a ductile or a brittle way.
Exactly. It's all connected.
So given all that, how do engineers actually measure a material's resistance to cracking?
Well, that's where a property called fracture toughness comes in. It basically tells you how much punishment a material can take before a crack starts to grow and become a real problem.
So a material with high fracture toughness is like a superhero,
Yeah.
able to shrug off those nasty cracks.
You could say that. And we have all sorts of tests to measure this, things like the Charpy and IZAD impact tests.
Tell me more about those. What do they involve?
Well, basically you take a notched specimen of the material and whack it with a pendulum. It's the very scientific way to break things. Then you measure how much energy it absorbed during the impact.
So like a controlled demolition derby for materials.
Something like that. And these tests are really useful for understanding how a material's fracture toughness changes at different temperatures. Remember that ductile to brittle transition we were talking about?
Yeah, the one that sank all those ships.
Right. Well, these impact tests can help us see exactly when that transition happens for different materials.
Okay, this is all making a lot more sense now. It's not just about choosing a tough material. It's about understanding how that material will behave under specific conditions.
Exactly. That's the heart of material science. Understanding how the structure and properties of a material dictate its performance, and then using that knowledge to create structures that are safe, reliable, and, well, don't fall apart at the worst possible moment.
Well said. This has all been super fascinating, but I feel like we've only just scratched the surface of fracture. And I know there's a lot more to learn about how things break down, but I think that's a good place to pause for now. We'll be right back after a quick break. Welcome back. Ready for round 2 of our material breakdown marathon.
Hit me with it. We've tackled fracture, and it's clear that even those tiny imperfections can have a huge impact on how something breaks. But I'm sure there's more to this story. What other ways can materials fail?
Oh, there are plenty, believe me. But let's talk about one that's responsible for a vast majority of failures in metal, shall we? It's called fatigue.
Fatigue. Huh. I feel like I've heard that term before. Doesn't it have something to do with repeated stress?
You got it. It's basically the weakening of a material due to repeated or cyclic stress. And what makes fatigue so sneaky is that the stresses can be way lower than the material's actual strength. It can fail even if it never really experiences a load beyond what it's supposed to handle. So it's like bending a paperclip back and forth until it breaks, even though each individual bend isn't that strong on its own.
A perfect example. It's death by 1,000 cuts, or in this case, 1,000 cycles. And the thing is, fatigue is happening all around us all the time.
Okay, now I'm starting to get a little nervous. So how do engineers even begin to predict when something might fail due to fatigue? It seems so random.
Well, it might seem random, but there's actually a pretty cool way to map it out. We use something called the SN curve.
The SN curve, huh? Sounds intriguing.
It's a graph, basically. It shows how the stress amplitude, which is the range of stress the material experiences, relates to the number of cycles it can withstand before it goes kaput.
So, like, if the stress is higher, it'll fail after fewer cycles.
You got it. But here's where it gets a bit more complex. You see, some materials, certain types of steel, for example, they have something called a fatigue limit. What that means is they can withstand a crazy number of cycles, like practically infinite, if the stress level stays below a certain threshold.
So it's like they have a built-in safety net against fatigue.
Yeah, you could say that. But unfortunately, most materials, especially a lot of those non-ferrous alloys like aluminum or copper, they don't have this fatigue limit. So even tiny stresses, if they cycle enough times, will eventually cause a failure.
Okay, so for those materials, it's all about figuring out how long they'll last under a certain amount of stress, like giving them an endurance test.
Precisely. We look at things like fatigue strength, which basically tells you the stress level at which a material will fail after a certain number of cycles. We're usually talking millions of cycles here.
Millions. Wow. Okay. But fatigue failure isn't just this single event, is it? It's more of a process, right?
You're right, it doesn't just happen all at once. Think of it like this. You have a tiny crack, maybe starting at one of those stress concentration points we talked about earlier. That's the initiation stage. Then, with each stress cycle, that crack grows a little bit longer. That's propagation. And finally, once it hits a critical size, boom, it spreads rapidly and you have a full-blown fracture.
So it's a bit like a ticking time bomb. But can you actually see any signs of fatigue before the final break, like any warning signs?
Sometimes, yeah. There are often some telltale marks left behind on the surface of a material that's been through a lot of fatigue. Think of it like clues left at a crime scene.
Ooh, I love a good detective story. What do these clues look like?
One type is called beach marks. Sometimes they're called clamshell marks. You can actually see them with the naked eye. They look like these concentric ridges kind of radiating out from where the crack started. Each one forms when the crack's growth pauses for a bit, like when a machine is turned off.
So each beach mark is like a chapter in the story of that crack's growth.
Exactly. And then you have these even tinier marks called striations. You need a microscope to see those. Each one represents a teeny tiny bit of crack growth that happened during a single stress cycle.
Wow, that's amazing. We're literally talking about microscopic evidence of fatigue. But I have to ask, it seems like fatigue is pretty hard to avoid. I mean, things are constantly being stressed and strained in the real world. So is there anything engineers can do to make materials more resistant to this kind of wear and tear?
Absolutely. We've got a few tricks up our sleeves. One of the biggest ones is designing components in a way that minimizes those pesky stress concentrations we talked about. Remember, sharp corners and sudden changes in geometry are the enemy.
So smooth curves and rounded edges are a good thing.
You got it. Think of it like streamlining a car to reduce drag. By smoothing out the flow of stress within a material, we can make it much tougher.
Makes sense. But what about the material itself? Can you actually do anything to the surface to make it more resistant to cracking?
We can. There are some pretty clever surface treatments out there. One of my favorites is shot peening.
Shot peening, what is that exactly?
Well, it's a bit like giving the surface a tough love massage, actually. You basically bombard it with tiny, hard particles at super high speeds. This creates these compressive stresses in the surface layer, making it much harder for cracks to form.
Okay, I can see how that would make it tougher. Are there any other surface treatments like that?
Oh yeah, there's case hardening. For that one, you add carbon or nitrogen to the surface layer of a steel. It's like giving the material a suit of armor. Makes it harder and way more resistant to wear and tear.
So you're basically strengthening the material's outer shell.
Yeah.
Very cool. But what about the environment? We talked earlier about how temperature can make some materials brittle. Are there other environmental factors that come into play with fatigue?
Oh, for sure. Corrosion is a big one. Think about all those metal parts that are constantly exposed to moisture or salty air. That stuff can eat away at the surface, creating all these little pits and cracks. And you guessed it, those can act as stress raisers.
Sounds like a double whammy. The corrosion weakens the material and then makes it easier for those cracks to form.
Exactly. And then you have thermal fatigue, which happens when you repeatedly heat and cool a material. All that expansion and contraction creates stress, and eventually you get fatigue cracks.
So it's like the material is getting a workout, but it's a workout that eventually wears it down. Are there any ways to protect materials from these environmental villains?
Definitely. For corrosion, we use things like protective coatings, choose materials that are naturally more resistant to corrosion, or try to modify the environment itself. And for thermal fatigue, we try to minimize those temperature swings or choose materials that don't expand and contract as much when heated and cooled.
So it's all about managing the material's interactions with its surroundings, making its life a little easier.
You got it. But we've talked a lot about fracture and fatigue, but there's another major player in the material failure game that we need to address.
Bring it on. What's this next villain on our list?
It's called creep. And it's a bit of a slow burn compared to the dramatic stuff we've been talking about with fracture and fatigue, but it can be just as destructive over time.
Okay, I'm intrigued. Tell me more about this creep phenomenon.
Creep is basically the tendency of a material to slowly deform under constant stress. It usually happens at high temperatures, think jet engines, power plants, that sort of thing.
So it's not about sudden breaks, it's more about gradual deformation over time, like a slow motion breakdown.
Exactly. Imagine you have a weight hanging from a metal wire. At room temperature, the wire stretches a little bit and then stops. But if you heat that wire up, it'll keep stretching even though the weight hasn't changed.
Whoa, okay. So it's not just the load itself, it's the combination of load and temperature that really matters here.
You got it. Creep is all about time. The longer the material is under stress at high temperature, the worse it gets. It's like a slow motion marathon for the material.
A marathon that it's eventually going to lose. Are there different stages to this creep marathon, so to speak?
There are, actually. Creep usually happens in 3 distinct stages. The first stage is called primary creep. In this stage, the creep rate, which is basically how fast the material is deforming, starts off pretty high but then gradually decreases.
So it's like the material is putting up a fight, trying to resist that deformation.
Exactly. It's trying to hold its own. This resistance comes from something called strain hardening, where the material actually gets stronger as it deforms. But eventually, that strain hardening reaches its limit, and we move on to the second stage, which is secondary creep.
Okay, so what happens in secondary creep? Does the material just give up at that point?
Not quite. In this stage, the creep rate becomes constant. It's like the material has found its pace, you know? It's still deforming, but it's doing it at a predictable rate.
So it's found its rhythm.
Exactly. And this steady-state creep rate is a super important parameter for engineers. It helps us predict how that material is going to behave over the long haul. But this steady state, it doesn't last forever. Eventually, the material enters the final stage, which is tertiary creep.
Tertiary creep. Uh-oh, that doesn't sound good.
It's not. In this stage, the creep rate accelerates like crazy, and the material is basically heading towards failure. This failure, we call it rupture. It's basically when the material breaks apart because of all that accumulated creep damage.
Okay, so we have primary creep where the material's resisting, secondary creep where it settles into a steady pace, and then tertiary creep where it all goes downhill fast and the material finally breaks.
You got it. And remember, all of this is happening under constant stress, so it can be pretty insidious. But don't worry, just like with fracture and fatigue, engineers have come up with ways to predict and prevent creep failure.
This is all so incredibly complex. I mean, how on earth do engineers even begin to figure out how material is going to behave under all these different conditions?
It is complex, but luckily we have some pretty amazing tools and techniques to help us make sense of it all.
Okay, we're back and ready to wrap up this material failure marathon. We've covered fracture, fatigue, and now creep. It's pretty amazing how many different ways things can fall apart, right?
Yeah.
And these processes, sometimes are happening super slowly, and sometimes it's all over in the blink of an eye.
It really shows you that materials are way more dynamic than we tend to think.
Definitely. But with all this talk about failure, I have to ask, is there anything we can actually do to prevent this stuff from happening? Or are we all just doomed to watch our bridges and airplanes crumble around us?
Not doomed at all. That's where the real fun begins, actually. The ingenuity of materials science and engineering. We've got a whole toolkit of strategies to fight back against fracture, fatigue, and creep. It's like a never-ending chess match against these material menaces.
Okay, I like that. I'm game for a good challenge.
Yeah.
So what's our opening move? What can we do to protect these materials?
Well, one of the most important weapons in our arsenal is something called non-destructive testing, or NDT for short. It's basically a way to look inside a material and find defects without, well, destroying it in the process.
So like a health checkup for materials.
Exactly. It's like giving the material an X-ray or an ultrasound. We use things like sound waves, magnetic fields, even thermal imaging to find those hidden cracks and weaknesses before they have a chance to cause any trouble.
That's pretty cool. I imagine that kind of testing is super important for things like airplanes.
You bet. In aerospace, every single part of an airplane, from the wings and fuselage to the engines, goes through rigorous NDT inspections throughout its entire life. It's all about making sure those tiny cracks don't have a chance to grow into something dangerous.
Right. You definitely don't want any surprises at 30,000 feet.
Yeah.
What about other industries? Is NDT used for other types of structures?
Oh yeah, it's essential for things like pipelines, bridges, power plants, anything where failure could have really serious consequences. It's all about catching those problems early before they have a chance to turn into disasters.
Okay, so NDT helps us find those hidden flaws. But what about predicting how stress is going to affect a material in the first place? Can we do that before we even build something?
We can, and that's where computer simulations come in. We use a technique called finite element analysis, or FEA, which basically allows engineers to create a virtual model of a part and see how it behaves under different loads.
So it's like a digital stress test.
Exactly. We can apply forces to that virtual model, simulating real-world conditions, and the software will show us exactly how the stress is distributed within the material. It's like having a crystal ball for material failure.
That's amazing. So you can see where those stress concentrations are lurking and adjust the design before you even build anything.
Exactly. It's one of the biggest advantages of FEA. We can optimize designs, make sure materials are being used efficiently, and ensure that the structure is going to be strong enough to handle whatever we throw at it.
Okay, so we have NDT to find existing flaws and FEA to predict how stress is going to impact a material. But what about those long-term processes like fatigue and creep? How do we predict those?
Well, for fatigue, we use those SN curves we talked about earlier, combined with statistical models. It's all about calculating the probability of failure under specific loading conditions.
So we're basically playing the odds, figuring out how likely the material is to get tired and break under repeated stress.
That's a good way to put it. We take into account things like the stress range, the frequency of the cycles, the material's properties, even environmental factors like corrosion, to estimate how long that part should last before it needs to be inspected or replaced.
What about creep? How do we predict that slow, steady deformation over time?
For creep, we do a lot of testing and modeling as well. We run tests at different temperatures and stress levels to see how the material behaves over time, and then we use that data to predict how it's going to creep at lower temperatures over much longer periods.
So it's kind of like creating a creep fingerprint for each material.
You got it. And this kind of long-term prediction is especially important for things like power plants, where components operate at high temperatures for decades.
This has been such a fascinating journey. We've gone from these tiny microscopic cracks all the way up to massive bridges and airplanes, from the sudden snap of a brittle fracture to the slow creep of metal under heat.
And it's amazing to see how the stuff that makes up our world, even the seemingly mundane things, are actually so complex and full of hidden stories.
Absolutely. So as we wrap up our deep dive here, what's the one big takeaway you'd like to leave our listeners with? What should they remember about all of this?
I'd say this. The next time you see a bridge, an airplane, or even just a simple paperclip, take a moment to appreciate all the science and engineering that went into making sure it stays in one piece. And remember, even though things break, our understanding of how they break is what allows us to build a safer and more reliable world for all of us.
Well said. Thanks for joining us on this deep dive into the world of material failure, everyone. It's been a wild ride. And we'll see you next time for another adventure in knowledge.